In an equation such as this that contains the quantum number, it is important to remember which state the quantum number J stands for. In this case, we are considering absorption. J stands for the quantum number of the lower energy state. To be consistent with the definition of J for the emission of the transition, we will be written as E of J plus 1 going to E of J. And the energy difference will have the same magnitude but a negative sign, indicating that energy is lost. J still represents the quantum number of the lower energy state. It is typical to use the equation 14.21 for absorption and emission spectroscopy and just keep track of whether light is absorbed or emitted. Equation 14.21 is commonly written in terms of rotational constant B, factoring out 2 from the terms involving the J equation. Equation 14.21 can be rewritten as delta E is equal to 2B times J plus 1. For absorption spectroscopy, the minimum J value is J is equal to 0. So by considering specific values of delta E versus the value of J, delta E sub 0 to 1, 2 times B times 0 plus 1 is equal to 2B. Delta E sub E 1 going to 2 is equal to 2 times B times 1 plus 1, which is equal to 4B. Delta E sub 2 to 3 is equal to 2B times 2 plus 1, which is equal to 6B. Delta E sub 3 going to 4 is equal to 2B times 3 plus 1, which is equal to 8B. And last, delta E going to from 4 to 5 is equal to 2B times 4 plus 1, which is equal to 10B. Figure 14.8 shows the graphical representation of a type of rotational spectrum for linear molecules. Figure 14.9 shows a diagram of energy levels and the allowed transitions that are labeled. Compare the two figures. You should be able to find specific transition between figure 14.9 that corresponds to the line that figure 14.8 suggests by the above equations. The spectrum consists of a series of equally spaced lines, spaced by the amount equal to 2b. The spectrum will be a series of equally spaced lines only if the unit of display is directly proportional to energy, like frequency or wave number. If the spectrum were displayed in terms of a quantity inversely proportional to energy, like wavelength, then the lines of the spectrum would not be spaced equally. This illustrates the necessity of understanding the unit used to display a spectrum. The above equations show something else about rotational spectrum, its relationship to B, but which in turn is related to the moment of inertia. For diatomic molecules, the moment of inertia is defined simply as mu r squared, where mu is the reduced mass and r is the internuclear separation of two atoms. Rotational spectroscopy is therefore useful in calculating the sizes of diatomic molecules. This is a general capability of rotational spectroscopy and is most easily illustrated for diatomic molecules. Pure rotational spectra usually occur in the microwave region of the electromagnetic spectrum, so the phrases rotational spectra and microwave spectra are sometimes used synonymously. The lines of the rotational spectra are also expressed using several typical units, as the above example showed. In the microwave region, it is typical for historical, habitual, and practical reasons to express transition in units of frequency. The microwave region frequencies are in megahertz or gigahertz range. It is not unusual to see rotational spectra displayed using frequency units. Figure 1410 shows the pure rotational spectrum in terms of frequency. Rotations frequently occur along with vibrations, which is why we use vibrational spectra. So it is also customary to express the rotational transition in a common unit of vibrational transitions. The wave number in centimeters to the negative first, figure 14.11 shows the rotational spectrum in terms of the wave number. There is a potential problem with the rotational spectrum. It is displayed in terms of wavelength because wavelength is not directly proportional to energy, and the consistent spacing of rotational levels is not obvious. Figure 1412 shows the same spectrum as figure 1411. But in terms of wavelength units, the equal spacing isn't obvious, despite the fact that each spectrum illustrates the same information. This will be discussed further in our treatment of vibrational spectra later in the chapter. Rotational spectra, like those found in figures 1411 and 1412, show an interesting intensity pattern. The intensity pattern of rotational spectra is due to the number of molecules having a certain rotational state. This is called population of state. Because the population of each rotational state is different, the number of molecules absorbing radiation and becoming excited to the next state is different. This population difference is responsible for the varying intensities of each rotational spectral line. The temperature determines the population of rotational energy levels. Rotational levels are close enough to energy that thermal energy is sufficient to cause some molecules to be excited in their rotational states. Therefore, there is an increased probability of a transition from those excited rotational states to the level at the next highest in J. At some values of J, however, the ability of thermal temperature to thermally populate rotational levels decreases. A statistical treatment of energy levels indicates that the approximate maximum populated J quantum number, J sub max, is J max is approximately equal to KT over 2B to the 1/2 power. Where K is the Boltzmann constant, 1.381 times 10 to the negative 23rd joules per Kelvin. T is the absolute temperature of the sample, and B is the rotational constant expressed in units of joules in this equation. The expression is in part due to the fact that the degeneracy of the rotational levels is 2J plus 1. If it were not, then the lowest rotational intensity patterns as seen in figures 1411 and 1412 would not appear. Equation 1423 is an approximation, as quantum numbers J is limited to the whole numbers, and some rounding off is usually necessary in the above equation. 1423 allows one to estimate the temperature of one gas phase sample from its rotational spectrum. The effect of a temperature on a population of energies will be a major topic of chapter 17. The energy of each rotational state has a degeneracy of 2J plus 1 due to the possible values of M sub J. However, the presence of the strong electric field in the particular direction, molecules rotating with different quantized values in angular momentum in that direction, indicated by the M sub J values, will have a slightly different energy. Absorptions or emissions due to rotational state transitions will appear to split into larger numbers of lines. and the particular number of lines for each spectrum will be determined by the delta m sub j is equal to 0 or plus or minus 1 selection rule. The phenomenon is an example of the Stark effect discovered by German physicist Johann Stark in 1913. In 1919, Stark was awarded the Nobel Prize for his discovery. This effect is another case of behavior that is classical mechanics and why it could not explain what quantum mechanics could. Examples of splitting shown in figures 1413 and 1415. It is not important to note that the Stark effect depends on the z component of the angular momentum defined by m sub j and is not dependent on the figure axis component of the angular momentum identified with k. Molecules that don't have a permanent dipole moment are rotating, of course, but they do not follow the gross selection rule for pure rotational spectra. Their rotations cannot be observed directly using microwave spectroscopy. We now examine the rotational spectra of symmetric top molecules. The values for rotational energy levels are given by equations 1416 and 1417 for symmetric tops. The given selection rules for the change in J, K, and Mj quantum numbers were given by the following equations, 1418 and 1420. As with linear molecules, since m sub j does not affect the rotational energy, it will have no effect on the rotational spectrum unless the molecules are subjected to a strong electric field, that is, the Stark effect. Since the selection rule for k, that is, it must remain unchanged, delta k is equal to 0, the difference in rotational energies is dictated solely by changes in j. Delta E sub E of j going to E of j plus 1 is equal to E parentheses j plus 1 parenthesis close minus E parenthesis j close is equal to 2b parenthesis j plus 1 close equation 1424. This equation is for absorption of electromagnetic radiation by either a prolate or an oblate top, where b is the rotational constant as it appears twice in the three rotational constants for symmetric top. Remember, one of the rotational constants for this unique and different are the other two. This is the same expression we determined for linear molecules. Again, the quantum number J refers to the lower energy state involved in the transition. This suggests that we can determine little more about the surface structure of the symmetric tops other than the single rotational constant, even though symmetric tops have two distinct rotational constants. If molecules acted like perfect rigid rotors, this would be the case, but they are not perfect, and that does allow us to obtain additional information from real spectra. We will be able to get this in the next section. By definition, molecules are spherical tops, and they do not have a permanent dipole moment. So, they do not have pure rotational spectrum. However, under some circumstances, they may have rotational absorption superimposed in their vibrational spectrum.